In section 7.4, we're going to learn how to compute formal charges. We're going to use those formal charges to identify the most reasonable Lewis structure. And then we're going to explain the concept of resonance, and we're going to draw some Lewis structures to represent resonance. Starting off with formal charge. The formal charge of an atom is a hypothetical charge if bonding electrons were distributed evenly between the atoms. So we know that that's not true. We know that some of those electrons participate in bonding and are necessarily associated with just one nucleus. But we're going to imagine what if they were. We can use these formal charges to choose the correct Lewis structure when two or more options seem equally likely. And if we're going to express formal charge mathematically, the formal charge is going to equal the valence electrons minus all of the lone pair electrons minus 1/2 of the bonding electrons. The formal charges of all atoms in a molecule will sum to the molecule's overall charge. So let's look at an example with iodine tetrachloride here as an anion with a -1 charge. We're going to start off by taking iodine because it's the one that's different than the others, right? We're going to put it in the center. That's our central atom. We're going to draw a bond to each of the 4 chlorines, okay? Then we're going to start to divide the bonding. Then we're going to start to assign the lone pairs of electrons to their atoms. Each chlorine atom now has 7 electrons assigned to it, and the iodine has 8. Okay, so we're trying to get octets here. Each one of these chlorines has 1, 2, 3, 4, 5, 6 electrons, plus both of the electrons in the bond count towards its octet. It now has 8. Iodine, on the other hand, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's actually hypervalent right now. It doesn't even really like to be in this kind of a situation, right? If we take a look at the formal charges, we're going to start off with the amount of electrons we expect iodine to have from its group in the periodic table. We got 7 here, okay? If we subtract out half of each one of the bonding ones, so 1, 2, 3, 4, plus all of the non-bonding ones, 5, 6, 7, 8, we get that 8 value there. If we did that same math for chlorine, we would get 7. We see that the formal charge on iodine is -1. The formal charge for chlorine is 0. We add those two together, we get -1, which is the charge that we expected this molecule to have. If we look at a different example here, we have bromine trichloride. Again, we're going to start with bromine. We're going to form bonds to each one of the chlorines. We're going to start to assign one of the electrons or the lone pairs to each of their atoms. We're going to do it such that chlorine has 7 electrons and bromine has 7 electrons. We start to do our math for the formal charges this time, and we see that we get 0 and 0. And so they all have a formal charge of 0, which sums to the neutral species bromine trichloride. Okay, we're going to start off by defining a phrase here. We've got molecular structure. This is the arrangement of atoms in a molecule or ion. You may have noticed that when we're drawing the Lewis structures, we can wind up with multiple different possibilities. More than one of these structures may be viable, but some are inherently unstable and won't form. We can use the formal charges to determine which of these are the stable ones. So what we're going to do to maximize stability is we're going to have favor structures in which all formal charges are 0 as being preferable to one where there's some non-zero formal charge. If the Lewis structure must have a non-formal charges, the arrangement with the smallest non-zero formal charge is preferable. Lewis structures are preferable when adjacent formal charges are 0 or of opposite sign. When we must choose among several Lewis structures with similar distributions of formal charges, the structure with the negative formal charges on the more electronegative atom is preferable. So let's look at some examples. We could have CO2. We could draw 2 double bonds to the oxygen and have a 0 formal charge on each one. If we do a triple bond to one oxygen, though, and a single bond to the other, we wind up introducing formal charges, and we don't want that. If we, instead of putting carbon in the center, put oxygen in the center, we also introduce even larger formal charges, meaning that that's not going to be very stable either. So considering the stability rules, the only really likely candidate out of these is going to be CO2 written that way. If we look at a little bit more difficult example here, we have thiocyanate ion, we have a carbon, a nitrogen, and a sulfur. It's not really necessarily clear which order they should go in, but when we start to work out their formal charges, we see that putting carbon in the center with sulfur at one end and nitrogen at another leads to the least formal charges. So this leads us to resonance. What a resonating structure is if you look at an example like our nitride ion, right? We could have a double bond going to this oxygen, or we could have a double bond going to this oxygen here. If that were true, then what we would see experimentally is that one of these bonds is shorter than the other bond. But in actuality, that's not really true. If we measured this bond and this bond, they're the same length, and they're roughly equal to 1.5, like a bond of 1.5. So what exactly is happening here? To justify this, we're going to introduce the concept of resonance. So when 2 or more Lewis structures with the same arrangement of atoms can be written for a molecule or ion, the actual distribution of electrons is an average of that shown by the various Lewis structures. The individual Lewis structures are called the resonance forms, and the actual electronic structure of the molecule with resonance is called the resonance hybrid. So we're going to use a double-headed arrow in the center to indicate that these are resonance structures. And we will realize that the actual electronic structure is never described by either resonance form. So this is never really going to exist, and this is never really going to exist. What's going to exist is a resonance hybrid that is a combination of the two. There can be more than just 2 resonance forms, as seen here with CO3, carbonate, anion. Here we have this double bond that's moving around the carbon. If we were to measure these bond lengths, we'd actually find that they'd be close to a bond of 1.3. In section 7.5, we're going to describe the energetics of covalent and ionic bond formation and breakage. We're going to learn about the Born-Haber cycle, and then we're going to use average covalent bond energies to estimate enthalpies of reactions. So the strength of a covalent bond is measured by the energy required to break them, separating the atoms participating in the bond. Bond energy, or bond dissociation energy, is the energy required to break a covalent bond in a molecule in the gas phase. When a single bond is broken, the bond energy is the same as the standard enthalpy change of the reaction. So we saw this before. We see now that if we have X bound to Y, we break that bond, we're going to get a bond energy that is going to be equal to the change in enthalpy, standard change of enthalpy for that reaction. So each bond type has its own associated bond energy. Shorter bonds have greater bond energies. Longer bonds have lower bond energies. Double bonds are stronger than single bonds. Triple bonds stronger than double bonds. Adding multiple bonds therefore decreases the bond length and brings the nuclei of the bonding atoms closer together. Here we have a table of some common bond energies and bond lengths. And we can see that the shorter bond lengths lead to higher energies, whereas longer bond lengths have lower energies. So we learned about the standard enthalpy in Chapter 5. There we were using standard enthalpies of different reactions in order to calculate the standard enthalpy for a specific reaction. We can do this exact same thing with bond energies. And it has a very similar form where we're going to add up all the bond energies of the bonds broken. Those are positive values. And we're going to subtract out all of the bonds formed. Here are the bond energies for various different bonds. This is a table that you're going to see in your book, table 7.2, and you're going to need this guy for the homework. So you should go check that one out in the text. Let's consider the following reaction. We have methane, and we're going to break that down into a carbon atom and 4 hydrogen atoms. We're putting energy in to break those bonds. We see that our delta H, or standard enthalpy, is positive. Since bonds are only broken, the standard enthalpy is positive. The overall enthalpy change is 4 times that of a CH bond. We can consider the formation of hydrochloric acid. Here we've broken an HH bond and a ClCl bond, and we formed two HCl bonds. Our bonds broken are going to be for the energies of the DH and the ClCl bond. We're going to subtract out from that the energy in that HCl bond. Notice that we didn't change the sign of any of the bond energies. We just inputted into the formula and we multiplied it by how many there were, and we wind up with a negative value of negative 185 kilojoules. So we could expect this to be a spontaneous reaction, to happen all by itself and release energy. Ionic bonding. So we know that ionic solids are made out of different ions that are held together in a lattice. So the energy that's holding that lattice together is called the lattice energy. Note that separating the ions requires energy, an endothermic process. Therefore, lattice energy values will be positive. So we're going to expect positive values for this. So we have an equation for calculating the lattice enthalpy. However, it's really pretty hard to make this calculation for any given lattice. Determining what this C constant is for your specific lattice is pretty tricky. But just by looking at the form of this, we can make some generalizations. Ions with higher charges, meaning that this Z plus value or Z minus value are higher, are going to have higher lattice energies. So are atoms with lower atomic radii, meaning that this R naught value down here is going to be smaller, making the whole ratio larger. The Born-Haber cycle is a special application of Hess's law that offers an alternative method for calculating lattice energies. The lattice energies can be calculated from other known enthalpy values. So what you need to know is the enthalpy of formation of the compound, the ionization energy of the metal, the electron affinity of the nonmetal, the enthalpy of sublimation of the metal, and the bond dissociation energy of the nonmetal. If you knew all of those things, then you can put it into this equation here and calculate the lattice energy. Keep in mind that lattice energy cannot be measured directly like bond energy. We have to do several different measurements, or we have to rely on calculating it using the first equation. But we can get at it using this value here. And here is the overall diagram. So what we want to get is to this piece right here. So if we're able to add up all of these values and then subtract out this value here, we can get this missing piece here, which is the lattice energy. section 7.6, we're going to predict the structures of small molecules using valence shell electron pair repulsion, Vesper theory. We're going to explain the concepts of polar covalent bonds and molecular polarity, and we're going to assess the polarity of a molecule based on its bonding and structure. So with the Lewis models, we've been looking at two-dimensional representations of molecules, but molecules are three-dimensional objects. So in order to fully represent the molecular structure, we must be able to describe the bond distances, bond angles, and relative arrangements in three-dimensional space. So bond angle. If we look at our planar acetone down here, the bond angle is going to be the angle between any two bonds, right? So this is a bond angle. There's going to be a bond angle here, and there's going to be one here. This one happens to be about 118 degrees. And then we have our bond distance. This is the distance between the center of the two nuclei on these atoms. And here you can see this represented using 1.21 angstroms. We usually use angstroms or picometers, where an angstrom is 10 to the minus 10 meters, or a picometer is 10 to the minus 12 meters. Valence shell electron pair repulsion theory, Vesper theory, enables us to predict the molecular structure, including approximate bond angles around a central atom. Predictions are based on the number of bonds and lone electron pairs in its Lewis structure. Vesper assumes that electrons in a valence shell will arrange themselves in order to minimize the repulsion between electrons, and it does that by putting them as far away from one another as possible. Vesper is usually able to predict the correct arrangements of the molecules, and it does this only by taking into account the electron-electron repulsions. So the way that the nuclei repel each other, the way that the electrons attract to the nuclei, these are not considered in the Vesper theory. Let's look at an example. The Lewis structure of this molecule predicts that beryllium will have two bonds and no lone pairs. In order to separate the electron-rich fluorine atoms, Vesper predicts that we're going to have a linear arrangement with 180 degrees between them. In practice, we would see that this is actually true. We're just going to place these two fluorines as far apart as possible. Here we have a very important table that you guys are going to have to come back to, where we describe what's going to happen as we add different regions of electron density around central points. So remember that these could be atoms or they could be lone pairs. And what's going to happen, so when we have two regions, we get a linear structure. When we got three regions, we're going to get this trigonal planar. So it's all on the same plane. Then once we have four, now we're getting into three-dimensional structures, such as the tetrahedron here, where this hydrogen is in the back and this one is in the front. If you guys are having kind of trouble picturing any of these, I suggest you go and Google tetrahedron, which is a shape, and you'll see exactly what this is here. If you have trigonal bipyramidal, you're going to wind up with this kind of structure, which is pretty unique because if you look here, there's a difference between the bond angles here. So any one of these three along this periphery here are 90 degrees apart from the top ones and 120 degrees apart from one another, whereas these top ones and the bottom one here are 90 degrees away from all the others. Okay, so these ones here at the periphery with 120 degrees between them, those are called equatorial positions. And the ones on the top and the bottom are called the axial positions. And we're going to see in a moment that that can be kind of important. Once we get up to 6 regions, we're going to get this octahedron shape where all of our atoms, electron regions are 90 degrees apart. Molecular structure is a geometry of a molecule that depicts all the atoms in 3D, but electron pair geometry is the 3D geometry that includes all of the atoms and all of the lone pairs. So here we can see that this is an electron pair geometry because it's got the lone pair described there, Whereas here, we're omitting the lone pair and we're only showing these atoms and how they are arranged. I mentioned before that we use these wedges here to depict a hydrogen that's coming out of the plane of the paper, or the screen in this case, and we're going to use these dash lines to depict hydrogens that are inside of the plane facing away from us. You're going to see this kind of notation used extensively in organic chemistry if you continue to go on. So some regions of electron density repel one another to a greater extent. So lone pairs and lone pairs, so two lone pairs interacting with one another are going to repel each other more than a lone pair would with a bonding pair. And bonding pair interactions are going to be even less. Okay, so this leads some regions of electrons to occupy more space than others. So we're going to think of lone pair as being a big space. It's a big thing that's occupying a lot of space. Triple bonds are a little less, double bonds a little less, single bonds being taking up the least amount of space. And the regions that occupy more space will push neighboring regions, leading to slight variations in the bond angles. So let's take a look at that. In this example here, we have our trigonal planar here, and everything's 120 degrees apart, giving us 360 degrees all the way around. But when we put in this lone pair, we're going to expect that these two are going to get squished together a little bit, and we're going to have less than 120 degrees. Similar here, in a proper tetrahedron, they're all 109 degrees apart. However, when we put the lone pair here, it pushes all three of these down a little bit, and we're going to get less than 109 degrees here. Again, if we put two lone pairs here, they're going to really repel each other a lot. That's going to push these two much closer together. We're going to expect that we're going to get much less than 109 degrees. This would be this situation in something like, say, water. Here we have our trigonal bipyramidal, and you can see that we get our 120 degrees here and our 90 between the equatorial and axial points atoms. When we put in a lone pair, it starts to push these guys closer together, so that these now have less than 120 degrees apart, and this is even less than 90 degrees. And this leads to a very asymmetrical shape that we call the seahorse or seesaw. If we put in two lone pairs, we're going to see that we actually wind up with something that has 90 degrees apart from all of these. And then if we put in a third lone pair, we're going to arrange these two 180 degrees apart from each other. Notice that as we added these lone pairs, they always went into the equatorial positions, and they always will. So that's an important thing to note, that these positions are not the same when we're dealing with the trigonal bipyramidal arrangement. And that's reiterated here. And here we can picture the axial versus the equatorial positions. The Vesper procedure. The first thing we're going to do is we're going to write out the Lewis structure of a molecular polyatomic ion. Second, we're going to count the numbers of electron density, the lone pairs and bonds around the central atom. A single, double, or triple bond counts as one region of electron density in this case. Third, we're going to identify the electron pair geometry based on the number of regions of electron density. And you're going to do that by going back to this table in conjunction with this table here. Fourth, we're going to use the number of lone pairs to determine the molecular structure. If more than one arrangement of lone pairs and chemical bonds is possible, we're going to choose the one that will minimize repulsions. In trigonal bipyramidal arrangements, repulsion is minimized when every lone pair is in an equatorial position. In an octahedral arrangement, the two lone pairs, repulsion is minimized when the lone pairs are on opposite sides of the central atom. So molecular polarity and dipole moments. So we saw earlier with our formal charge that pure covalent bonds can lead to partial charges, which we can abbreviate with this sigma plus, meaning a partial positive charge, or sigma minus, a partial negative charge on the bonding atoms. This separation of charge gives rise to a bond dipole moment. A dipole moment is a vector. Vectors are essentially mathematical representations of an arrow with a direction and a magnitude. Our dipole moment vectors are going to point towards the more electronegative bonding atom. The magnitude of the vector, given by mu, is dependent on the magnitude of the partial charges and the distance between the charges. So we can see that as the distance increases, the dipole moment is going to increase. We pull those two charges apart, inputting energy, which is going to yield a higher dipole moment. And when the partial charges are larger, we're going to get a higher dipole moment. What Q here is mathematically would be the difference between the partial charges. If you subtracted the positive one, or if you subtracted the negative one from the positive one. Dipoles with large magnitude are written as vectors of greater length. So here we can see we have carbon and hydrogen. There's not a huge difference between them, so we get a smaller vector. And by difference, I mean the difference in their electronegativity. Here we have boron and fluorine. There's a very large difference in their electronegativity. We get a larger dipole moment. So for diatomic molecules like we just saw, it's pretty easy. We only have one bond, okay? And the polarity of the whole molecule is described by that single dipole moment. Molecules with a net non-zero dipole moment are called polar molecules. So we're going to see that we can combine those bond dipole moments together to get a molecular dipole moment. When that molecular dipole moment is not zero, we get a polar molecule. And to do that, we have to sum our vectors. So let's talk about what vector summation looks like. You guys may have seen this in physics. If I have vector A and I have vector B, the sum of them is going to be vector C. How do I know that the sum is C? Well, if I put these two heads to tails, then it's going to start off at the origin of the C, and it's going to end at C, okay? So what we're seeing here is that if I move B up so that its tail meets A's head, and then come over, I get C, and that it doesn't matter if I move B up or if I move A over. Both of those arrangements are going to yield the same vector C. We can do it with more than that, more vectors. So here we have F, D, and E. Their summation is G. And any way that I want to arrange those, heads to tails, I'm still going to wind up with G. So sometimes these bond dipole moments can cancel. In this case where we have symmetry and they're opposed to each other, they're going to cancel each other out, and the whole overall dipole moment for this molecule is going to be 0. But sometimes they don't. So in the case of water, we have a dipole moment heading here towards oxygen, one heading here. If I picture moving this over, such that it was heads and tails with this guy, I'm going to get this resulting dipole moment, which is the dipole moment for the whole molecule. Sometimes the dipoles can oppose each other but just have different magnitudes, in which case you're going to wind up with a dipole moment that's smaller than this one, but you're still going to have an overall dipole moment for the molecule. Okay, so polar molecules are going to align themselves to external magnetic fields. Polar solvents will better dissolve polar solutes, okay? So this is the like dissolves like sort of thing. nonpolar solvents are going to dissolve nonpolar solutes. Polar solvents are going to dissolve polar solutes. Here we can picture this electric field thing. So we have these molecules, they're floating around, and they're just arranging themselves in any old way, you know, whichever way they feel like at any moment, they're moving, and these arrangements are changing all the time. Once we apply that external electric field, though, all of the partial negative charges are going to face the positive end here, this positive plate, and all of the partial positive charges are going to face this negative plate, and we get a very coherent, aligned situation. This is only going to happen, though, in the gas phase or in a liquid phase, where these molecules are free to move about and not trapped in a solid lattice.